Hello, today we're continuing with A-Level Physics Revision series, and we're continuing in our consideration of sensing devices, in this case direct sensing devices, and this is part 2 of the series of videos. In the last video we looked at the role of the operational amplifier in effectively putting a little bit of logic into the circuit to determine whether, for example, to switch a light on or off, or to turn the thermostat on or off. I now want to cover what happens if you feed back part of the output from the operational input into the amplifier again. So you have some mechanism for taking the output from the operational amplifier and feeding back a fraction. That fraction is beta, where fraction that's going to be a half or a third or whatever it may be. And you feed that back to the input. There's some means of adding, so there'll be some kind of device here which adds this and feeds it back into the input of the operational amplifier, which has a gain, you'll remember, A0. Well, in essence, the output voltage is equal to the gain times the input. And that is equal to the gain, A0, times V in, which is the input coming here, plus beta V out, because the proportion of the output voltage is being fed back into the input. So not only have you got the input voltage, but you've also got a proportion, beta, of the output voltage being fed back in again. So the total input is V in plus beta V out. And that's multiplied by A0, the gain, to give you an output voltage. And if you rearrange, you'll get that V out into 1 minus A0 beta is equal to A0 times V in. And that can be written as V0 divided by V in, that's V out divided by V in, equals A0, the gain, divided by 1 minus A0 beta. And there are operational reasons why you might want to do it. It gives you an increase in the range of frequencies, it gives you less distortion, and it gives you greater operational stability. Next we move on to an inverting amplifier. This uses the operational amplifier in the following way. There's the inverting and there's the non-inverting. We have a resistance here, which we'll call the input resistance. We have a line which is earthed, and we have a resistance which we'll call RF, and that is joined to the output of the operational amplifier. This, of course, is the overall V output, and this is the overall V input. I'm not actually going to draw the power supply for the amplifier itself. We know that you'll need to connect that to a battery, but let's leave that out so it doesn't get too complicated. Now remember that the difference between the voltages in these two inputs here must not be very great. If it is, then the amplification factor will mean that the whole thing will just become saturated, and the output voltage will simply equal the voltage of the battery that is powering the operational amplifier. So the difference between these two voltages has to be very small. This voltage, you can see, is 0 because it's connected to the earth. And that means that this input voltage must be very close to this voltage. Well, that voltage is 0, so this voltage must be almost 0, and that's why this line here is called a virtual earth, because it's virtually at 0 volts. Now, one of the important qualities of an operational amplifier is that its input resistance is extremely high, which means that for all practical purposes no current flows along these two lines here. So any current coming along here past this resistance is going to flow that way round the circuit. If the input voltage is positive, then the current is going to flow this way. If the input voltage is negative, in other words, the other way, then the the current is going to flow this way. But look at the input voltages and the output voltages. Let's say the input voltage is positive. Well, that will mean that the voltage at this point, V minus, will be larger than V plus, because V plus is, remember, 0. And V minus must be some small amount larger than that. And that means that V minus is greater than V plus, which means the output voltage is going to be negative. So in fact, when Vi is positive, when the input voltage is positive, the output voltage is negative. And it gets the other way around as well, of course. When the input voltage is negative, the output voltage is positive. In other words, whatever that voltage is, up or down, this will be the opposite. And that's why it's called an inverting amplifier. Now let's consider the current that is flowing. It will depend on the voltage which way it flows, but just for this example, let's take the current that's flowing. We've said that all of it, or pretty much all of it, is going to go this way because there's such a high resistance to the operational amplifier that no current flows through the amplifier. So the current is going to go through here. So the current that goes through resistance R1 is the same current that goes through resistance RF. And so you can say that the current is going to be the voltage divided by the resistance. So the current through R1 is going to be the PD across R1 divided by R1, and that's the current that goes through R1. But the current that goes through RF is going to be the PD across RF divided by RF, because the same current goes through both, and current is voltage divided by resistance. What is the voltage across R1? Well, it's V input minus whatever this is here. But I've just told you that's a virtual earth, so it's 0. So the voltage across R1 is V1. So V1 divided by R1 equals the potential difference across RF. What's the potential difference across RF? It's that voltage minus this voltage. But that voltage is 0. So it's minus V out divided by RF. And that you can simplify as minus, oh sorry, not minus, we'll do that. V out divided by V in, no minus sign, V out divided by V in is equal to minus RF divided by R in, or R1. So the voltage out divided by the voltage in is the same proportion as the value of that resistance divided by the value of that resistance. That was the inverting amplifier. This is now the non-inverting amplifier. Once again, we take the operational amplifier, which will of course have its power supply, which we won't bother with. We have the minus and plus terminals. We've got the output. And here, what we're going to do is to take we have a resistance and we have another resistance. We'll call this RF and we'll call this R1. This is the earth. Move that up a little. Turn it round a bit, and then here this is the input voltage, that's V in, and this is the output voltage, V out. And then we know that V out is equal to the amplifier gain times V plus minus V minus, V plus minus V minus. But what is V plus? V plus is simply V in. So that equals A naught into V plus, which is V in, minus V minus. What is V minus? V minus is the output voltage, but it has been put across this potential divider here. So in fact we're going to call that beta V naught, where beta is R1 divided by R1 plus RF. It's just a potential divider. Okay, it's R1 divided by the total resistance is that value of V naught, which is fed back as V minus. And so we've got that V out is equal to the amplifier gain into V plus, which is simply the input voltage, minus V minus, which is that proportion that's going across R1 that's being fed back to V minus. So that's our formula. And now it's just a case of going through the maths. That means that the V out equals A naught V in minus beta A naught V out. Bringing V out onto one side, you've got V out into 1 plus beta A0, A naught, equals A naught V in. So V out is equal to A naught V in divided by 1 plus beta A naught. And if you divide top and bottom by A naught, you get V in divided by 1 over A naught plus beta, because beta times A naught divided by A naught is beta. Now, if A naught, that is the amplifier gain, is very large, then this term here reduces to 0 and you get V in divided by beta. But beta, we've already shown, is R1 over R1 plus RF, and so V0 is VI times the inverse of beta, which is R1 plus RF divided by R1, which is V in into 1 plus RF over R1. And so now we can say that the ratio of the output voltage to the input voltage is equal to 1 plus RF divided by R1. And this term must be positive, and therefore V0, or rather V out and V in, must be the same sign. They're either both positive or they're both negative. And that means it's non-inverting. If the input voltage is positive, the output voltage is positive. If the input voltage is negative, the output voltage is negative. Well, let's just remind ourselves where we've got to. We started off by identifying that we can have a sensing device which usually changes resistance as the thing that you're measuring varies. And then we said that you can put that sensing device into an electronic circuit which somehow also contains an operational amplifier, and that will produce you a voltage which is either positive voltage or a negative voltage. And the trick is that what you want is the voltage to change direction when a certain key point is passed with the sensing device. So if it gets too dark, you want the voltage to change so that that will then trigger a light being switched on. If the room gets too cold, the sensing device gets too cold, then you want the resistance to change such that the voltage changes direction so you can switch the thermostat on. And that therefore brings us to the next bit of the debate, which is how then do you get things switched on? How do you switch on the light? How do you switch on the thermostat? And the answer is that you do not want this circuit to be part of a circuit that might be having a very large current. For example, supposing you want to turn on an immersion heater, which might have a current of several amps going through it. You do not want this circuit to be part of that circuit, because then you'll have the potential for a very high current to go through the operational amplifier, and that will destroy it. And so we have to use what's called relays. What that means is that the circuit of which the sensing device and indeed the operational amplifier is a part will come to some kind of device here that will cause a switch over here to switch on. So somehow the action of the sensing device and the operational amplifier will cause this, whatever this is, to make that switch close. And that switch, of course, could then switch on a light or a thermostat or anything you like. And that process whereby a change here causes that switch to close is called a relay. And the best thing to use for that is an electromagnet, something which will not be magnetised until a current flows through it. But when a current flows, this becomes magnetised and causes the switch to close. And here's a simple way of doing that. Here is the operational amplifier output. Here is the earth line, and therefore the voltage out. From all the diagrams we've drawn in the past, they are all on this side of the line. This is now the output voltage, and what we're now going to do is to connect this to a diode and then to our electromagnet, and on this side we're going to have the switch, which is part of an entirely different circuit. Somehow in here we've got some gobbledygook. We're switching on lights, we're switching on heaters, whatever it may be. This is the business. The electromagnet will cause the switch to open or close, as the case may be. And we're going to have a return diode in the circuit this way. Now you can see that if V0 is negative, then no current will flow in this direction. No current will flow in this direction either, because the diode only allows current to flow downwards. So if V0 is negative, the current would like to flow upwards, but it can't because of that diode. Consequently, no current flows at all. Now, if back here the sensing device means that the polarity of the voltage changes, it changes from minus to plus, and we now have a positive voltage, then the current flows through the diode into the electromagnet. The electromagnet will cause the switch to close. So for example, let's say you needed to switch on a light in a room when it gets dark. You would arrange for your sensing device and your operational amplifier to generate a negative voltage so long as the light is strong. And that means whilst the light is strong, no current flows down through this diode. But as soon as darkness comes and the room gets dark, then the sensing device will change its resistance such that the combination of that plus the operational amplifier and the circuitry reverses the polarity from a negative voltage to a positive voltage. As soon as you get a positive voltage, the current flows, the electromagnet then works and flips the switch and the light comes on. What's the reason for that diode? Well, when it gets light again the following morning, this voltage is going to flip to become negative again and the current will stop flowing. The the electromagnet will stop, but there is often what's called a back EMF, which can damage the circuitry. And so what this diode does is it allows that electromagnet to discharge without causing any trouble to the operational amplifier back here. Of course, because the diode is that way round, the current, when it does flow through this arm, cannot go that way because it can't go through the diode in the wrong direction, and so the current is forced to go through the electromagnet. Now, pretty much any device, electronic device that you buy these days will make use of light-emitting diodes. So when you switch a device on, you know it's on because a little red light will come on. That is nearly always a light-emitting diode. And you can in fact get light-emitting diodes of different colours, red, green, yellow and amber. I have covered this to some extent in my videos on atomic physics. But two key qualities of light-emitting diodes are they don't take as much power and they are much more robust than, say, a filament lamp. So let's just consider a simple way in which they could be used. Here is the earth. Here is the operational amplifier output, which has come from the sensing device and the operational amplifier this side. And this is the voltage, which may be positive, it may be negative. How do we know which? Well, we might have, say, a resistance and then a light emitting diode which emits, say, red light if that is working, and then here's another resistance here with a diode going the other way emitting, say, yellow light. And what that tells you is if the voltage is positive, then a current will flow in this direction, but it won't flow in that direction because it can't get past the diode. It's the wrong way round. So the current will flow this way through the, let's call that the red diode, and that red diode will then glow. If at any stage the voltage flips, so the voltage is now negative, pointing in this direction, that means currents will flow upwards. Well, they can't flow upwards here because that's the wrong direction for the diode, so they flow upwards through this diode, which is, say, the orange. So what you've got now is if the red light is on, that means you've got a positive voltage and the current is flowing that way. If the orange light is on, that means you've got a negative voltage and the current is flowing that way. The final thing to recognise is that, as we said, with sensing devices, where usually the resistance changes as whatever you're measuring, it might be the temperature, it might be the light, it might be the pressure, whatever it happens to be, the resistance will vary. But as we said, it doesn't usually vary in a straight line. It usually varies in some kind of curve. And that means that if you want to say that you want the light to come on, let's say, when the lighting level in the room gets to that value, if this is a measure now of the light, then you want that resistance to be the critical resistance which will cause the operational amplifier's output to change from, say, positive voltage to negative voltage. And the only way you can do that is to calibrate the sensing device first. So there's no straight line. You'll actually have to work out at what point you get a particular resistance that coincides with the critical temperature or lighting conditions or pressure, where you want the, as it were, the resistance to go through the key point. And then you have to set up your circuit such that as the resistance passes this point one way or the other, when it gets to that point, the effect is that the operational amplifier's output flips from being positive to negative or vice versa. Hello, today we're continuing with A-Level Physics Revision Series, and we're continuing in our consideration of sensing devices, in this case direct sensing devices, and this is part 2 of the series of videos. In the last video we looked at the role of the operational amplifier in effectively putting a little bit of logic into the circuit to determine whether, for example, to switch a light on or off, or to turn the thermostat on or off. I now want to cover what happens if you feed back part of the output from the operational input into the amplifier again. So you have some mechanism for taking the output from the operational amplifier and feeding back a fraction. That fraction is beta, where fraction that's going to be a half or a third or whatever it may be. And you feed that back to the input. There's some means of adding, so there'll be some kind of device here which adds this and feeds it back into the input of the operational amplifier, which has a gain, you'll remember, A0. Well, in essence, the output voltage is equal to the gain times the input. And that is equal to the gain, A0, times V in, which is the input coming here, plus equals A0, the gain, divided by 1 minus A0 beta. And there are operational reasons why you might want to do it. It gives you an increase in the range of frequencies, it gives you less distortion, and it gives you greater operational stability. Next we move on to an inverting amplifier. This uses the operational amplifier in the following way. There's the inverting and there's the non-inverting. We have a resistance here, which we'll call the input resistance. We have a line which is earthed, and we have a resistance which we'll call RF, and that is joined to the output of the operational amplifier. This, of course, is the overall V output, and this is the overall V input. I'm not actually going to draw the power supply for the amplifier itself. We know that you'll need to connect that to a battery, but let's leave that out so it doesn't get too complicated. Now remember that the difference between the voltages in these two inputs here must not be very great. If it is, then the amplification factor will mean that the whole thing will just become beta V out, because the proportion of the output voltage is being fed back into the input. So not only have you got the input voltage, but you've also got a proportion, beta, of the output voltage being fed back in again. So the total input is V in plus beta V out. And that's multiplied by A0, the gain, to give you an output voltage. And if you rearrange, you'll get that V out into 1 minus A0 beta is equal to A0 times V in. And that can be written as V0 divided by V in, that's V out divided by V in,